Okay, so we've now at time equals 0, the wave function is an eigenstate. Okay, and then we substitute, and the Hamiltonian acting on psi 0 is equal to h. Remember, the Hamiltonian now has two terms, the unperturbed plus the perturbation acting on psi 0 at time equals 0, which is the eigenfunction. Okay, the eigenstate. Okay, so now if we look at this, h sub 0, the unperturbed Hamiltonian acting on an eigenstate just gives you the energy E sub n. Okay, and so we factor out psi sub n. We have it 1 minus, remember 1 over I is equal to minus I times h sub 0 acting on psi n is En psi n times delta t over h bar. Okay, so so that accounts for this and this. Okay, and now we basically are left with minus I delta t over h bar times the perturbation part of the Hamiltonian, which is again operator acting on the eigenfunction psi sub n. Now, because psi sub n is not an eigenfunction of the perturbation of the perturbed Hamiltonian, then this in general does not give you just back the eigen energy. Okay, the eigenvalue. Okay, so this term here is just the usual time dependence for the unperturbed Hamiltonian. Remember when we did the expansion of the wave function when it's in an eigenstate, when the system is in an eigenstate, we did the expansion of the temporal part of the wave function, which is just a complex exponent. We expanded the complex exponent to second order in time, and here is that same result back, but just to first order in time. Okay, 1 minus I En delta t over h bar. Okay, so this is basically, so this acting on psi sub n is just it's the usual time dependence for the unperturbed Hamiltonian, and so this does not change the physical state of the system. However, this part over here, okay, this is the perturbation term, and basically this operator acting on an eigenfunction of the unperturbed Hamiltonian, okay, this function will give you a different wave function. Okay, and we know, since the psi sub n's are a complete orthonormal set, that is, that any function can be described as a linear superposition of each one of these eigenstates, then we know that this new function, this new wave function, which is this operator acting on an eigenfunction psi sub n of the unperturbed Hamiltonian, will give us a new wave function, and it can be described by a superposition of the eigenstates of the original system. Okay, so that is minus I delta t over h bar times this new function, okay, omega psi sub n, is equal to the superposition of eigenstates of the original Hamiltonian. Okay, and the coefficients can be found. Remember, what we do is we just project the new state. There should not be a star there. Okay, so I got rid of the star, so we project the new wave function onto the mth eigenstate of the original unperturbed Hamiltonian, and that gives us the coefficient, okay, of the particular coefficient of interest in that expansion. Okay, and from that we can calculate the probability of a transition, that is the probability of going from state n to state m, and that's just the coefficient squared, the magnitude of the coefficient squared, and so it's just given by the squared of this quantity here, of this